Hello all, welcome to a video discussing our final project on scalable manufacturing of batteries for electric vehicles and hybrids. So due to popular or unpopular demand, we have changed the scope of this project, reduced it so that instead of designing an EV and a PHEV battery and manufacturing plant, we're only going to choose one battery. There's only going to be one battery, one manufacturing plant, one analysis based on either choosing Ferrari PHEV or Rivian's either the standard, large, or max pack. So you're going to choose one of these four and then go down these series only once to describe the battery design, the cost and so forth, and the performance and the manufacturing and business case to as an exercise in scalable manufacturing. And the good thing is that it's all self-contained in this BatPac Excel spreadsheet, as we'll talk about now. And the plan for this video is to go down each of these bullet points, and I'll show you where in the spreadsheet you can pull out these values. So this spreadsheet itself, it's a very nice, very thorough and robust model of battery manufacturing, including starting all the way down from the cathode physics and cathode graphite electrolyte, and building all the way up to the cells, to prismatic sandwich cells, to modules, to packs, and all the packaging, the thermal management and stuff. It's all there in terms of performance, engineering, and costs, and manufacturing cost, manufacturing layout, all these processes. It's all there. So I highly recommend you look into the manual, the updates, the back other techno-economics papers, the physics behind it. That's all there for us to hopefully study as much as you can. But for the purposes of this project, I'll show you how you can, if once you get all that knowledge and experience, like I have worked with this a few times, how you can quickly design a battery and pull out all of this, run this analysis and pull out all of these answers to these bullet points in a straightforward manner. Okay, so the plan is, so as we talked about in class, we're going to get either a Ferrari plug-in hybrid or a Rivian electric vehicle. And as you know, the hybrid battery design is a much different specifications than an electric vehicle. So the plug-in hybrid is a supplement to the burning the fuel. And even though this is a really cool souped up Corvette, a really souped up Ferrari, and it basically operates the same as a Prius in the sense that the battery is much smaller because it's only a supplement to the fuel burning. And this Ferrari, the specs we can find online pretty quickly, it's 8 kilowatt hours, which results in 15 miles only electric, 350 volt operating voltage, nominal voltage, and then 180 kilowatt power rating. So that is what one thing to start off, like pretty much you can use this as a starting point in the BatPac model. But the electric vehicle has different specs because it's there's no fuel to burn. It's all charge storage from the grid or from somewhere. You'll charge your battery. And the standard battery pack is available for within the cost of the floor model of the Rivian. It's known to be 135 kilowatt hours, and the newer models are going to operate at 800 volts, but the kilowatt power rating is not known yet. The costs are known for manufacturer's retail price. The standard without any extra cost is built in, but then you can pay an extra $6,000 for 320 mile range. $16,000 for 400-mile range. Okay, so these are our starting points. So what I'm going to do is now share the BatPac model, and then I'll just keep the Excel sheet open on a share screen, but I'm going to go down each of these bullet points here. And so what I recommend is in this video to also open up this PDF for yourself so you can follow along this order that I'm going in, because I'm not going to share the screen for the PDF. I'll keep it on the Excel spreadsheet. Okay, so let's go ahead and go to the Excel spreadsheet, the BatPac. So here we are. This is the Excel spreadsheet. It's posted on Canvas. You can download as many copies as you want. And I'm not sure, yeah, you probably open them as long as you change the name. You should be able to open many. And I'll tell you now, the one reason why you would want to open many is if you want to study many battery chemistries, because it only lets you analyze one battery chemistry at a time. You would have to yeah, pretty much open another copy to change the battery chemistry without losing all of the other results of a different battery chemistry. Okay, but so let's go ahead and start. This is the default. It just opens up into this about page here, and then it has all of these huge range of tabs which go into the intricate details of the physics of the battery, the engineering of the battery, and the cost of the materials, all the way up to the manufacturing cost. It doesn't have details of the processes so much. It's just all built in that amounts to a cost at the end, and time and production rate at the end. And that will show you how you can answer these bullet points in the PDF pretty quickly from this spreadsheet. And it is overwhelming, and there is so much in there. And again, I recommend you to study this as much as you can. But for the purposes of this report, it's actually, I'll guide you guys on how straightforward you can pull things out with some experience that I have already, and I'll show you guys. So to start off, the dashboard is pretty much how you're going to design the battery. So this is the dashboard. We'll come back to this, but I'll tell you right now, the dashboard is where we're going to design it. Then all we need to do is then look at most of the answers to my questions and the most pertinent things for the design, as I expressed in these bullet points of the report, is that you can pull them from the summary of results and manufacturing cost. So these three tabs, dashboard, summary results, and manufacturing cost, are pretty much will give you everything you need to know. Okay, so let's go back to the dashboard. The first thing, one thing to quickly know how to navigate through this big involved spreadsheet. Again, after my guidance, hopefully you can, it's more manageable and less intimidating. The first thing is that what we're looking for is this aquamarine teal color here, because that's what we need to input to get a design going. So the teal ones, this is just to get the calculation. The first one, besides that, is the battery chemistry. And it's a pull down menu. You have to click on this arrow here to choose which battery chemistry you want. I hope it's easy for you to see here. You have to zoom in sometimes. And so that's the start of this whole thing, the battery chemistry. And like I said before, you only can analyze one battery chemistry at a time. And so you can either, you definitely can, one at a time, analyze these in terms of the battery chemistry, or you can open many Excel sheets at the same time and play with it that way, because these analyses only start from the one choice here. But besides that, oh, I just changed it. So it started off at something, I just changed it. But and then once you fix the battery chemistry and so forth, you can have an array of 7 different batteries to do a parametric study starting from the chemistry, cathode choice, then the electric vehicle choice, or this is choosing between electric vehicle or different types of hybrids. So in our report, we're just talking either about a PHEV or an EV. So this is where you fix that. So those two are you need each combination of electric vehicle and cathode chemistry requires its own analysis. So you can either open many Excel spreadsheets or not, and maybe you don't need to do that crazy analysis. I recommend it. We'll talk about the analysis itself soon, but it all starts from a fixed chemistry and electric vehicle versus plug-in hybrid. Yeah, so okay, so which chemistry to choose? Well, let's actually go to our lecture where we talked about this battery chemistry stuff. So the lecture slides have a pretty good summary of what is battery chemistry? Well, battery chemistry refers to the cathode of the battery, lithium ion battery. So lithium ion batteries transport lithium ions from the anode to the cathode while controlling the electrons across the load. It gets charged and discharged, running on electricity, on electrons. And each of these cathodes materials determines the performance to some extent, cost and performance. So you spoke about in class, there are many different types of lithium ion chemistries, starting from lithium cobalt oxide. That's mostly for devices. That's the first Sony battery. Then since that 30 years, we've been evolving into other types. So we're talking about electric cars in this assignment, and lithium iron phosphate, if we look at the bottom middle row here, for electric buses, lithium iron phosphate started off as applications for buses, applications for power, forklifts, and like more low power applications. But as we spoke about in class, Rivian and even Tesla, they're also going to adopt lithium iron phosphate. So there's the pros and cons. This is not the latest analysis of the performance, but the effect of choosing these chemistries is cost, energy, power, safety, temperature, endurance, and lifespan. So this is the ramifications of choosing these chemistries. They have different performances. So Tesla, they're always evolving. It's hard to pin down their chemistry because they have their own vertically integrated battery infrastructure. And so I would say that lithium iron phosphate is known. It's going to be the standard. Rivian, it's already known, as we talked about in class, that Rivian's next model years are going to have lithium iron phosphate as a starting point, but they're going to go to nickel cobalt aluminum oxide or nickel manganese cobalt oxide eventually, and trying to minimize the cobalt. So to summarize, it's either going to be LPO battery, NMC battery, or NCA battery. Okay, so that's why. And then what do these mean? Well, if we go to BatPac, incorporates these batteries in their spreadsheet. So if this pull down menu that we saw earlier on the dashboard of the spreadsheet has NMC 333, 622, 532, 811. Those are all nickel, manganese, cobalt with these different proportions of nickel, manganese, and cobalt. And you can see the stoichiometry there on the right. And those are in the BatPac model because these are valid or like established cathode batteries used in electric vehicles and hybrids. NCA is in the BatPac, this lithium, nickel, cobalt, aluminum with these proportions shown on the formula on the right. Lithium iron phosphate, and lithium manganese oxide. So the for the batteries purposes, the electric vehicles, the as we saw from that other slide, it's pretty much LFP, NCA, or NMC. Those are what we're going to play with in the spreadsheet there. Okay, so let's go another also let's go to the spreadsheet and I'll show you how to pull those down. Okay, so now we're back at the spreadsheet. Let's look at this list closer again. It's the teal version. This color is what we're changing. And the interesting thing about this spreadsheet is that it has many different types of NMCs, different proportions of their proportions of the nickel, manganese, and cobalt, but they also have power configurations and energy configurations. What those mean is, like one way to put it, it's hybrid versus electric vehicle, because for hybrid, it's used mostly as a power boost, as a speed boost, and energy, it's used as its main source. You need to kind of design it so that it can have the highest mileage, you know, the last the longest range. So that's the energy version. That's what those two mean. And then you see this dash G. Dash G means that graphite is the anode. So that's the industry standard now. They have anode graphite, but then as you see here, there's these other special ones here. It's lithium manganese oxides dash LTO. That's actually like a more exotic anode called lithium titanate. And we don't really have to worry about these. These are more exotic and less established, having a anode that's not graphite. And this one is kind of weird here as well. So so if you go all the way up this list and go down, these last three are probably going to be the only ones that wouldn't be worth playing with. But everything above that are viable batteries that are in the industry. Okay, so let's go to, I'm going to say the higher the nickel, the better. So lithium, NMC 333 means they're all the same proportion of nickel to manganese to cobalt. But what the Rivian news that we talked about in class was that they want to have the highest nickel that you can. Why? Because cobalt, it has a lot of it's hard to, it's very limited. Cobalt is more scarce than lithium. So people are trying to, for that reason, minimize cobalt use, and then it's also hard to get. There's a lot of humanitarian and business problems, economic and humanitarian challenges with cobalt. So a lot of companies are trying to go away from cobalt. So let's get the NMC design with the most nickel, and let's start from the energy. We'll do an EV. So we're starting with the highest nickel content of the NMC, because that's where that minimizes cobalt, and that's a trend in batteries in general, that you want to minimize the cobalt for the economic and humanitarian reasons. Now let's go choose the EV. That's there. Okay, so those two are fixed. That is that's done. But the next step is to go down to these other teal inputs, teal colored boxes, and what we see here is it's designed to make an array of calculations that for a given fixed chemistry and EV versus versus hybrid, you can then make an array of designs from 1 through 7. So that's what that's designed for. And then once you do that, as you see here, Control Shift R is good to press every once in a while to make sure when you make the changes, it's converging. It's all these calculations are cycling through and getting answers. So I did that, and then we'll talk about what that means. So I think now that we have those two, I'm going to go ahead and stop the recording so that we can divide this video into a couple of sections. So we'll let me stop this version and post another second video.